Now, construction of a tangent. How do we geometrically construct a tangent to the circle at that particular point on the circle using the geometrical instruments or the geometrical knowledge is what we're going to discuss for the session. It's quite easy because construction of a tangent is based on the recent theorem which we have discussed, which says that the radius is always perpendicular to the tangent at that particular point of contact of the circle. Therefore, using that property, let's see how a tangent can be constructed for a circle with suitable radius. So initially, let me start with the steps. So my step 1 says that draw a circle with center O. So I just draw a circle with center O is what is my step 1. Then I take a point P on the circle, any point P. Say for example, I take a point P on the circle so that I join OP. Clearly, OP is the radius which passes through the point P is how I get. Now for any point P on the circle, OP is the radius, and I assume this as the point of contact, then I want to draw a tangent to that circle. Now we all know that since the radius is perpendicular to tangent, so if I wanted to draw a tangent at the point of contact P, then I need to have exactly 90 degrees drawn from OP. So I put the protractor here, and then from this protractor I just try to measure the angle which is 90. Exactly marking the 90 degrees and just extending that line, I get the perpendicular line which is called the tangent. So this is how we construct the tangent to the circle at the point P, where my step 1 is drawing a circle with center O, and then my step 2 is joining O and P, and my step 3 is taking a protractor and exactly putting that at P and marking 90 degrees, and then extending the line along that 90 degrees. I get a straight line passing through P and perpendicular to OP, where this is called the tangent which is constructed for the given circle. This is how the tangent is constructed for a given circle with suitable radius. It's very simple. Construction of a tangent using the geometrical properties. Radius perpendicular to tangent. Now this construction makes me clearly understand that for every point there's only one tangent, because if I take the point on the circle and draw the tangent, I do not have two tangents which can pass through the same point. So this construction makes me come out with the learning outcome that at every point on the circle we can draw one and only one tangent to the circle. One and only one tangent, which clearly is evident through the construction as made. One point on the circle, only one tangent. No two tangents can be drawn from one point on the circle, is how we come with the learning outcome through the construction of a tangent using the geometrical knowledge. Now this topic is a continuation of the previous session of construction of a tangent. Interestingly, the difference being that I have to construct a tangent to the circle whose center is not known. So how do I locate the center for a circle and then find the tangent is the biggest challenge for this topic. So when the center is not known, obviously we don't know the radius, and hence we cannot base on the radius to draw a perpendicular line which will be the tangent, because radius is perpendicular to tangent. Now in this case, let's see how we can construct a tangent though the center of circle is not known. So in this case, let me take the steps which involve a circle. Let me take a circle whose center is not known. So I take the point P on the circle, say the point P on the circle is this. On any part of the circumference, I take here the point P on the circle. Then I join to get the chord. So let me take another point Q on the circle such that I join so that PQ is the secant or the chord of the circle. So with the construction of P and Q joined, with Q being a point on the other side of the circle, then with this I try to create the radius. How do I get the radius from this circle? Since we know that angle in a semicircle is 90 degrees, that is, when I take a circle and just divide it exactly half, then any angle made by the semicircle will be 90 degrees. Using the concept of angle in a semicircle is 90 degrees, this becomes the diameter. Therefore, I try to construct a semicircle using the property of angle in a semicircle is 90 degrees. Therefore, when I join P and Q, PQ being the chord, I can get the diameter this using, I can get the diameter AP if I can construct the angle PQA as 90 degrees. So immediately I put my protractor at Q, and then putting my protractor out here, I try to measure the angle 90, exactly the 90 degrees, and then extend. This out here. So when I extend this, this line tends to cut the circle at the other side as, say, I take it as R. I take this as point R. Now I get this to be 90 using the protractor. The measurement of angle is 90. Therefore, PQR is 90 degrees. Immediately, when PQR is 90 degrees, RP tends to be the diameter, because this is the property in a semicircle. Since the angle in a semicircle is 90 degrees, when I join this, I get this to be the diameter. So RP is the diameter of the circle. Now this being the diameter, exactly the middle of RP, take the measurement and cut the measurement into half, I get the center of the circle, which can be created from the angle in a semicircle. So dividing this into two parts by using the perpendicular bisector concept, I get this, and then more than half, and then I get the perpendicular bisector, which gives me the center as O. So this center O will give us the radius, which is nothing but the radius. And from radius, I can construct the tangent because radius is perpendicular to tangent. Therefore, put the protractor out here and then measure the angle. Then clearly, I get a line which is a tangent to the circle. So it's quite interesting that even though we don't know the center of the circle, initially we try to identify the center of the circle by joining the chord PQ, by locating some point Q on the other side of the circle and joining PQ, and then drawing a 90 degrees angle, we get a point, third point, which cuts the circle here, and then join PR, which is the diameter. Now to get the center of the circle is nothing but exactly half of the diameter. Therefore, I take more than half, and the compass is used to construct the perpendicular bisector. So with the perpendicular bisector, I get the center, which intersects the perpendicular bisector with the diameter. Now once I know the center, I know that OP is the radius, and therefore using my protractor out here, I measure the angle 90 and pass through P. Therefore, I get the radius perpendicular tangent. Therefore, this is how the tangent is constructed from the circle where the center of circle is not given. Is how we construct the tangent for a circle with an unknown center. Length of tangent. What do you mean by length of tangent for a circle? Because tangent is a line which extends infinitely on the left and the right. So what do we mean by length of tangent is the biggest challenge of the question. So to start with, let's take a diagram. I take a circle with center O and say I have my tangent at the point P. Say at P I have a tangent. Now, suppose I have this tangent which extends infinitely on the right and left. Then the length of tangent from, say, a point Q to the point of contact is said to be the length of tangent. That is, the length is referred as the distance of the point of contact from the desired point. So if Q is any point outside of the tangent or outside of the point of contact, then we have to find the distance between P and Q, which is called the length of tangent. So if I have this to be clearly the radius which is perpendicular, and this is say D, the distance from the point to the point of contact, then clearly when I join OQ, I get a right angle triangle OPQ, as can be clearly seen in the diagram. Therefore, length of tangent here is PQ, and I take this as D units. Now, since OPQ is a right angle triangle, immediately the Pythagoras theorem comes into existence. Triangle OPQ is right angled. That implies, by Pythagoras theorem, I clearly get OQ square equal to OP square plus PQ square. So by Pythagoras theorem, I get OQ square equals OP square plus PQ square. Then I take this. Let me take this as L, not D. So if I take this as L and I take this as D, let's see what exactly I get by substituting in the Pythagoras theorem. So to continue with, I get OQ square, which is clearly OQ being D, reduces to D square equals. So here in place of OP, I have R, which I am going to substitute on the right hand side as R square. Similarly, my PQ, which is clearly L, reduces to L square, is what I get when each of OQ, OP and PQ are substituted from the right angle triangle OPQ. Now, to continue further, because I need to find the length of tangent L, which is the topic of the session, therefore I take R square plus L square on the left and D square on the right, so that because I need to find L, my L square will be D square minus R square. That implies L is plus or minus root of D square minus R square coming as the root, but I don't take the negative value because length cannot be negative. Therefore, taking the positive value, L is root of D square minus R square units. So the length of tangent is given by the formula root of D square minus R square, where D is the distance from center of origin to the point outside the circle, center of circle to the point outside the circle, and R is the radius of the circle. So length of tangent can be found out if I know these two dimensions. Then the length of tangent is quite easy using the formula root D square minus R square units. Now let's see the number of tangents which can be drawn to a circle. As we have seen in the previous case, that when I take an external point, we have got the length of tangent from the point of contact. This is how we continue into understanding the number of tangents which can be drawn to the circle. Now there are three different cases which I am going to consider here for the number of tangents. The three cases being that if the line is cutting the circle, if the line is not cutting the circle, or if the line is touching the circle, then we'll see how different points are arised. Say for example, I have a circle with center O. Similarly, I have a circle with center O, and I have a circle with center O. Now for these three different circles taken with same center O, let me take the three cases where I take the point P initially lying inside the circle. I have the point P which lies inside the circle. I have a point P which is on the circle, and I have a point P which is outside the circle. So these are the three different cases where the point P is inside the circle, on the circle, and outside the circle. So clearly I understand that in this case I cannot draw any tangent, because when P is inside the circle, you cannot have any tangent which can be drawn at any part of the circle. Therefore, no tangent can be drawn through P to the circle, is how I understand the concept of a point lying inside the circle. Let's shift to the next case where the point P is on the circle. Now in this case, clearly I can see that there is one tangent which can be drawn to the circle passing through P. Therefore, in this case, I have one and only one tangent can be drawn through P to the circle as given here. So, no tangent and one tangent is how we get from the first two cases. Now let's shift to the third case where the point is exclusively outside the circle. Now since the point P is outside the circle, I can clearly see that the number of tangents I can draw from here are two. One coming out, passing through P. I have one tangent here which is T1, and I have another tangent which passes T2, are the two tangents which I can clearly see passing through P to the circle with center O. So in this case, I see that for any point outside the circle, there are two tangents which can be drawn. Two tangents can be drawn through P to the circle. So is how we understand the three cases where if P is inside the circle, there is no tangent which can be drawn through P to the circle. If P is on the circle, then there's only one tangent which can be drawn through P to the circle. And for P outside the circle, there are two tangents which can be drawn through P to the circle, as can be clearly seen through the respective diagrams. 2, 1, and no for inside, on, and outside the circle is how we understand the number of tangents connected with three different cases of the point P to the circle with center O. Now let's see a theorem which connects the third case of the previous session. As the third case says that if P is a point outside the circle, then there are only two tangents which can be drawn from an external point P to the circle with a suitable radius. Now, since these two tangents can be drawn, the theorem says that those two tangents, the lengths of those tangents will be equal. The theorem exclusively says that for the pair of tangents drawn, the pair of tangents drawn from an external point P, an external point P, external in the sense outside the circle, from an external point P to the circle have equal lengths, is what the statement clearly says. To understand more through the diagrammatic representation, geometrically we understand that if this is a circle with say center O, then from an external point or a point outside the circle, if I draw, we know that clearly we can draw only two tangents, tangent 1 and tangent 2. Then if I take this as A and B, then mathematically the statement says that the two tangents will have equal length. That is, this will be equal to this, implies PA is equal to PB is the property we identify in tangents connected with circles. Two tangents are equal if they are drawn from an external point to the circle. So let's see this proof of the statement through each of the construction of the given required to prove constructions and the proof. So let's see the proof of the given statement. So let's continue with the given part of the theorem. So in this case, I consider a circle with center O is what we consider initially. That is, I take a circle with center O. Now let P be a point outside the circle. So next, let P be a point outside the circle. So let me take the point P, which is outside the circle. Now, secondly, I come to drawing the tangents from P to the circle. Clearly, I see there are two tangents which can be drawn. As I see here, this is one of the tangent which is drawn, and this is another tangent which is drawn out here at A and B. So here I see that implies PA and PB are tangents to the circle which is considered with center O. Is what I get out here. Then thirdly, I join AO and OB, which can be taken as the construction. Here the construction is join OA and OB the radii. Now OA and OB are the radii, therefore they must be equal. Now since their radius is equidistant from any point to the center, therefore OA is equal to OB is what we have. Also, I join OP because this helps me in the further proof of the given statement. So I just join OP using the concept of O join with P. Now let's use some of the geometrical properties to understand on how we can prove that this is equal to this. So here finally, the thing what I need to prove is that there are equal tangents, or the lengths of the tangents are equal from an external point to the circle. Now since PA and PB are the tangents from external point P to the circle with center O, therefore I need to prove that PA is equal to PB. This equals this is what I need to prove in the proof of the theorem. So let's required to prove is PA is equal to PB is what I need to prove using the geometrical properties, the various geometrical properties in mathematics. So let's see the proof of this theorem continued. Now let's see the proof of the theorem where I need to prove that PA is equal to PB. So in this case, as I join OA and OB, which are equal because they are the radii of the circle, similarly, we know that they are perpendicular to the tangents because we know that radius is perpendicular to tangent. So first, OA is equal to OB initially, which is identified because they are same radii for the circle. Secondly, I find that these two are 90 degrees because radius is always perpendicular to tangent. Is the theorem what we have seen in the previous sessions. Therefore, OA is perpendicular to PA or AP, and OB is also perpendicular to PB is what we identify in either cases, because by theorem radius is perpendicular to the tangent is what we have seen in the previous sessions. Therefore, this perpendicular to this and this perpendicular to this. Now, as I see the diagram here, I identify two triangles here, OAP and OBP are two triangles which are part of the entire diagram. So I would like to take these two diagrams and show that they are congruent. My intention of showing the congruency will help me in finally making conclude that this is equal to this. So let's see how the congruency leads to the outcome of the proof or the final proof. So therefore, consider triangles. The first triangle here is OAP. Consider triangle OAP and triangle OBP are the two triangles which I consider. Now, as I clearly observe that the right angle out here is PAO, which is 90 degrees. Therefore, angle PAO of the first triangle is equal to angle PBO of the second triangle, because each one of them is 90 degrees, as already proved that this is perpendicular to this and this is perpendicular to this using radius perpendicular to tangent. So one of the angle is 90 degrees, which is right angle, is what we have from the two triangles. Similarly, I see that PO is the common length of the two triangles, therefore they are equal. That is, the length PO is equal to the length PO itself, because this is the common side for both the triangles, therefore they must be equal, common for two triangles. Interestingly, we also observe that this is the hypotenuse for both the right triangles which we have out here. So PO is the hypotenuse for the triangle OAP and PO is the hypotenuse for the triangle OBP, as can be clearly seen that this side is opposite to 90 degrees in either of the triangles. Therefore, this leads to the hypotenuse, right angle, hypotenuse, and let's see one of the side. Now, as I see in the two triangles, I see that OA is equal to OB because they are the same radii as given with the reason. Therefore, OA is equal to OB since same radii. We have already discussed in the previous session of this. So this is the side property. This makes us clearly reflect on the right hand Rhs congruency as we discussed in the topic of congruency in the previous sessions. Since Rhs is one of the congruency, therefore, since the right angle is equal, the hypotenuse are equal and one of the sides are equal, therefore, the two triangles are said to be congruent under Rhs congruency. Is how we conclude the congruency of two triangles using Rhs congruency property. Therefore, continuing from the previous part of the proof, I see that these two triangles are congruent by Rhs congruency. Therefore, by Rhs congruency, triangle OAP is congruent to triangle OBP as can be seen clearly. Now, since the two triangles are congruent, therefore their angles and sides must be equal in all respects. Therefore, the congruency makes us understand that all the sides and all the angles must be equal in their own respective manner. Therefore, the congruency gives us PA is equal to PB, and not only that, we also identify that angle OPA is equal to angle OPB, as can be clearly seen. The angle bisects. Now this PA equal to PB implies the lengths of tangents, as can be clearly seen from an external point to the circle, are equal. That implies the lengths of tangents from the external point P to the circle are equal, is what we conclude with the statement of the theorem, is how we get to the congruency, Rhs congruency of two triangles connected with the lengths of tangents equal. So whenever we draw an external point, we assume that these two lengths are always equal for any point outside the circle from where the two tangents are drawn. Also to note, there's a property we identify that PO bisects APB. Because of this property, also we get from the congruency that the line segment PO bisects angle APB. So angular bisector, what we call. So PO is the angular bisector of angle APB, is also which is identified from the congruency from the geometrical part of understanding each of the properties of congruency. Hence proved.